interesting stuff that you have seen yesterday, experimental device also about these things. And Anton Svetlichny will introduce the next speaker. So, Anton, please.
Give me a second. Yes, so can you, yes, yeah, okay.
Hello,
Oleksandr,
hello,
oh,
hello.
yes,
Hi,
great. So,
hello.
so, hello everyone. I'm glad to introduce the next speaker, Oleksandr Yakymenko. He is an associate professor at the Taras Shevchenko National University of Kyiv, as well as a visitor researcher and the University of Padua in Italy. And during his research career, Alexander Yakymenko was working with the different experiments and theoretical projects on the cold atoms, Bose-Einstein condensates, and exciton polaritons, moving the area of the Atomtronics. I personally have two publications with Alexander, and I want to say that he is a great researcher, and right now he is going to tell you about the introduction to Atomtronics and how can it be applied to the area of quantum sensing. So, Alexander, I'm happy to give you the floor.
Thank you for your kind words and for a nice invitation. So great to see you again and great to see all your audience. I hope you can hear me. Yes, it's okay. Can you hear me?
Yes, yes, we can hear you.
Okay, okay, great. So yes, I would
Yeah,
be happy
everything okay.
to. Okay, so I must admit that I'm theoretician, so maybe it's a bit disappointing, but I'm really like to collaborate with experimentalists. So I will mention some nice experiments today, but I'm not able to do experiment. And today I will talk about the such as fascinating field like Atomtronics. And first of all, uh, if you can see my screen, okay,
Yes, yes, we can see
great.
the screen.
Great. So the title is like Introduction to Atomtronics, and indeed I will start with some basic aspects of this subfield of quantum technology and what is this and why we need to introduce some new subfield and why it's important, why it's interesting. So Atomtronics indeed is a kind of part of quantum technology and it uses cold atoms, nickel cold atoms in some sophisticated, sometimes sophisticated engineered potentials, which allows information a very complicated structure and allows to to engineer, to structure, to realize some very interesting quantum devices, including sensors and some technology for quantum simulations as well, including both single atom and many body physics in different aspects. So uh, this is very developed field, and just to mention that there are a lot of papers, including review, and including one of the I was was participating as a cursor. So the roadmap of Atomtronics. But just to give you an idea, uh, what is the goal, so what is the subjects of Atomtronics, I will mention some of them. So formation of so-called matter wave circuits. So they allow to form some basic elements which um, can be used to transport to make some interference and design some more complicated mm, uh, systems, some devices which could be useful for different applications. So devices like what if we split Atomtronics, of course, it still seems to be relevant to electronics, of course. And indeed, in Atomtronics, there are experimental realizations of some elements which are similar to or equivalent to diodes, transistors, batteries, and squids, and so on. So then, of course, one of the important application of Atomtronics is quantum simulations. It's not only creating like qubits, but also formation of large arrays of single atom traps, traps with single atoms from each of them. Formation a really interesting system which could be potentially used for creating quantum computers. And of course, quantum sensing, which I will focus on today. This is one of the most intriguing and perspective application of Atomtronics, since I understand the quantum sensing is the subject of this activity, of this conference school. So this is very interesting application, because if you have the quantum system, coherent system, you can use the interference as which is really sensitive, as you know, from optics. Interferometers are here and there; they are very sensitive to different to different things. So you can measure, for example, rotation uses Sagnac interferometer. As far as I understand, you already had some lecture on that subject, and many different interferometers are very useful. But here in Atomtronics, the idea is to use interference of matter waves, so the broad wavelengths. And if you think about, for example, sensitivity of the, if you compare the kind of standard of technology interferometers based on Sagnac effect, when you have some waveguide with counter-propagating waves which can interfere due to the rotation, this is really sensitive. But if you do the similar stuff, I will give some details, with atomic circuits, you have a chance to increase the sensitivity by the factor which is proportional to the ratio of MC squared, so energy of the atom, related to the energy of the photon. So the 10 orders of magnitude. So it's amazing. And of course, if we can indeed proceed in this direction, so the perspective are very, very fantastic. But let's just to give an idea why sensing and atoms. Then, of course, quantum information processing, and you can use a coherent control and all this stuff which are related to the matter waves. And the last but not the least is the hybrid systems, which include the kind of integration of the atomic system, which are called atoms, with superconductors or optical system like photonic crystals, some metamaterials, and so on. So just to mention that this is very developed subject, and of course I'm not able to overview all of this subject, but I will focus on some problems which I was involved during the last years, and this is the outline of my talk today. So I will describe how these atomtronic waveguides are affected by curvature, and why it's important, and what happens if you have curved waveguides, and due to the coherence, and how it affects the density and phase of this coherent state. That's the first first part, and then I will switch to the to the linked rings. So I will consider different situation when they form planar system, like here, the two examples, one by one, side by side, and also concentric doubling system. Why it's interesting and why how we can use this system, for example, for measuring the acceleration. So it's kind of the idea, and some proof of the concept will be shown today. But first of all, I'd like to say a few words about vortices, which will be the kind of bridge between all the subjects which I will discuss today, because I'm really interested in vortices, which are universal structure in various physical systems in atmosphere, in space, and the vortices are everywhere. And just to mention that the vortices appears kind of building blocks of the turbulence. So the left, the piece of painting of Leonardo da Vinci, and this is kind of classical turbulence. So Leonardo, this is a water which flows to some fountain, I don't know, but it's clearly seen some vortices. And indeed, the vortices are kind of building blocks of the turbulent state, and it's very important. And also, not only the classical system, classical, like in other words, but also in quantum system. In quantum physics, you have some very intriguing behavior of these vortices because they are only one possible excitation, the sound, and these vortices, the excitation in quantum systems. And that is why the interaction between the vortices drives the turbulence and makes this turbulence very specific. But a few words about turbulence in general and why vortices. We will see today a lot of different examples of vortices, but something which we meet every day. So, like formation of the turbulent state, like here in this nice video from Japanese group, which is flight dragon forms these flows, and we see that some laminar flows are broken into some turbulent state, and we see some vortices here and there. And the cascade of these vortices forms a so-called Kolmogorov cascade, which means that if you have some income of the energy at the large scale, then due to the transformation of these vortices, which is described in this nice small poetry, so big rolls have little rolls which fit in the velocity, little rolls have lesser rolls, and so on to viscosity. So sorry for my English, but I think that you get the idea. So from uh, large scale perturbation, like you use this effect when you use your spoon with a cup of coffee, just trying to get it sweet faster, yes, not waiting for diffusion. So the vortices are kind of universal object, and we meet this object in classical systems, but in quantum systems they are even more important sometimes. So just to understand what is the difference, what is the main difference between just rotation and vortex flow, let me show these plots, which I have borrowed from Wikipedia. This is a rigid body rotation, which is quite familiar to you. So this is an angular velocity, and the linear velocity is related to the omega, like the omega cross r. And if you calculate the curl, or if you calculate the rotor of this vector field, you will get this 2 omega, which is quite familiar to you. And if you do the same, but with the vortex flow, which is described by this field, omega, you can see that omega is zero. What does it mean? You expect that, okay, so of course, the vortex is with some rotates, but if you have a look at these small balls, blue and red, you can notice that the blue balls, when they circle, yes, they change the direction of the axis. Yeah, you can see it. If you do the same with the vortex flow, what you can see, these balls have the same direction. So if you have this calculation, simple calculations clearly shows you that the the rotors of this field could be zero, but in some important cases, when the topology of the system is changed, you can get the non-zero value of this circulation. So, of course, you know that in quantum mechanics, the phase of the wave function is relates to the velocity field because you have the flow in so which is related to the wave function like this, and is the density, and there is a density, Vs is a velocity, and means if you calculate such a circulation, so you can see that is zero for single connected manifold. But if you have some holes like this, is not kind of uses the Stokes theorem is wrong. It's invalid here. And if you calculate the same, what does the circulation mean? So it is kind of orthogonal condition. So the momentum product of m and velocity is nothing but momentum, linear momentum. And if you calculate the circulation, you will get such a quantization rule. And m is an integer which is called the topological charge. And you can see that this structure appears when you have some kind of hole, some 0 points where the density is zero. It is very important. So this structure are in some sense topologically protected. It means that it's not possible to create the single vortex in the bulk of the system. It's not possible. It's kind of the mathematical theorem, which is called also the Kelvin theorem. So, but you can produce two vortices with opposite topological charge, or you can just invite one vortex from periphery, from outside, which will come and will create this hole in the bulk. So this is very important to understand what vortex is, because we will discuss these vortices. And by the way, this is again from Wikipedia. So this rotation is not homogeneous in radial direction. So this red dashed line is the vortex core with the density zero. And you can see that the flow is faster close to the core, and it's the case with the distance when you fly away from the core, the flow is slow. Okay. Well, this gives a very intriguing physical manifestations in superfluid systems. At first, system which was discovered in like a macroscopic superfluid system is, of course, the helium, liquid helium. If you just compare the impact of the rotation on the classical system, like if you have some cup of water and you try to rotate it, you will get kind of huge vortex which will fit the angular velocity which you apply to the system. But if you have the superfluid system, it's quite different because the angular momentum, the system gains the angular momentum by quantum, by quantum, which is called the vortex line here. This is analog of because of vortices in superconductors. But here, this is this vortex is a quantum of angular momentum. If you have a lot of such vortices, the total flow will tend to the similar like solid body rotation. But for few vortices. It's quite different. These vortices form lattice, and this is kind of this photograph photo of the real experiment with helium. These small white dots. It's kind of indication of the formation of the vortices. And by the way, it was used some very tiny pieces of ice, no, not the water, but of hydrogen, which appears like small crystals in the region when the vortex core forms. So this is to visualize it. The people use such a very clever idea to make it visible. So, because this is very small. In helium, this is few angstroms, and we will discuss the atomic gases. It's quite different situation, but the physics is very similar. Okay, so now I switch to new era, which started in 1995 when two groups in MIT and NIST has discovered, experimentally realized the Bose-Einstein condensate of atoms. And this is kind of iconic picture, what this picture means. So this is distribution momentum space, and the temperature decreases in the direction. So at some temperature, you can clearly see formation of coherent state. So the atoms, a macroscopic number of atoms drops to the ground state, to the single state, and this structure forms the coherent multi-wave object, which is we called Bose-Einstein condensate. And just a few words about how it can be done. As far as I understand, you have some lecture about laser cooling. If I understand, this is will be tomorrow, or it was done. I don't know. John, what is the idea? So I think that I can just have a brief overview of the idea, but I will not in position. I am not in position to come to the detail. So, but how to reach the state when how to reach the state when you have this and when this have Bose-Einstein condensate? What is the temperature you need to get to understand this? Let us imagine that you have some atoms, and of course you can consider the related de Broglie wavelengths, and if the distance between between the atoms will be of order of the de Broglie wavelengths, then these wave packets will overlap, and this can be easily used to estimate the critical temperature. So just let us estimate the distance between atoms, like cubic root of density of the atoms, and then you immediately gain this formula, which I have borrowed from textbooks. So as you can see, the mass is in the denominator. So this means that for atoms, this temperature is very small, and this of order of 100 nanokelvins. Nano, it's 10 to the minus 9. Yeah, so it's really cold. How to get such a temperature? So, and there are two stages to gain this temperature, the so-called laser cooling. The idea of this is very simple in principle, but of course technically it's very fascinating, but it's doable. The idea is to use a Doppler effect, and it means that if you have the atoms which have some energy, but the laser that is tuned in such a way that the frequency does not match the resonance. Resonance appears only when the atoms move in the direction to the source of laser. So this Doppler effect shifts the frequency, and when you emit the photon, the energy of the kinetic energy of the atoms decreases. So it's very clever idea, and it allows to get the temperature like hundreds nanokelvin, hundreds microkelvin. Sorry, not how to get nanokelvin. It's for this you can use so-called evaporation cooling. What is evaporation cooling? This idea is the same as you do when you try to cool your cup of coffee. So you just create some flow of the air, and you move away the particles, the vapor which appears at the top of your liquid, and then the temperature decreases. And the same idea, not the same, but basics, the physics is the same, is used to gain this nanokelvin temperature, tens or hundreds nanokelvins. You will lose some atoms, but you have some in the condensed state. So it's the idea of formation. And why? Again, the motivation of to do this very different aspects of quantum technology become available with these cold atoms. For example, this is shows some experimentally realized systems from atom lasers, which with different approach was realized. What is atom lasers? Is a coherent source of matter waves, and also some measurements with interferometry of the coherent matter waves, like shown here. And what is this? So if you can see this is, sorry, this is a tau in the Bremen. Sorry, so what is going on? This is a human being. So this is a box. It can be dropped, and in free fall, in this ball, there are some condensates which interact, and due to the interference patterns, you can measure very, very small effects of general relativity. For example, it was done experimentally. And this is example of so-called transistor. This is not so-called. Indeed, this is kind of transistor. If you have such a triple well potential, for example, you can use this kind of transistor because you can control the flow of atoms by small current of atoms in one of the wells. So you can increase the flow through these barriers by controlling it like a transistor. Another example is, for example, simulation of solid state physics in optical lattices. So you can create a periodic system with some defects or whatever. You can consider the quantum effects in such a periodic system, which are associated to the discovered in solid state physics. But here you can control with lasers and with atoms, and you can see the details, and which is very interesting for physical simulations. And another example is formation of the persistent currents, and I will discuss this in more details, just to show that this is one of the experimentally realized systems. Okay, so let's go ahead, and how the in experiment you can see the condensate. The condensate is one of the smoking gun of the Brazil state condensation is following. So if you have kind of a donut like this, and for example, if you have in a trap like shown here, and you switch off the trap, you consider time of flight, shadow when you use some laser beam to see some density distribution. It is remarkable that if at the beginning, if you have some squeezed, for example, like here, squeezed donut, like in vertical direction, after some evolution, you will see the formation kind of needle instead of donut, you will have the needle in the same direction. Why? Because of quantum effects, because of quantum pressure, which makes this ballistic expansion asymmetric, because the pressure was asymmetric due to the squeezed wave function. So it's kind of a clear demonstration of the coherent state. Another demonstration of coherent state, of course, vortices, and these vortices has been demonstrated in condensate as well. And so this is nice illustration with these dots, which are now, the size of these dots is already micrometers, not strange that micrometers, it's huge. But again, you can see this in time of flight like a lattice. It was very clear demonstration of the fluid state. Well, I think that just to explain how the theorists, why they're happy with this system, because you have a very dilute gas, and it means that you can consider the system with some kind of scattering theory at first born approximation, which gives very, very simple equation, which is called Gross-Pitayevsky equation. This is a mean field approximation. It means that you replace the body treatment by some effective mean field. And this gives us effective nonlinear potential. And what is important that you can control the behavior of the system with external trap. And this external trap could be, for example, magnetic, because atoms can have some magnetic dipole moment, or it can be optical trap, which can be either attractive or repulsive depending on the frequency. This is so-called red and blue detuned laser beams, which means that this factor, which describes which coefficient before proportional to the intensity of the laser beam, you can see that this is alpha can change the sign, and the omega zero is a resonance frequency. And if you tune the frequency, you can control either you will have attractive or repulsive potential. And due to this, you can create very, very detailed and complicated traps. For example, here is kind of a photo which is created by the atoms distributed in a trap. So this is Bayer and Einstein photo. So this is size in micrometers. You can imagine what is the accuracy of this experimental setup. Well, and why? Why we should care? So why you need these traps, all this stuff? I promised you to say something about the sensor, about rotation sensor, and one of the example is the experiment which realized a so-called atomic gyroscope, which means that you can measure the rotation frequency using this atomic circuit. What is shown here is in the same scale, this huge cylinder with human hair, like in the same scale. The size of this ring is kind of 20 micrometers, and the temperature is below 100 nanokelvins, and number of atoms is 10 to the 5. And what happens here? What happens here in this system when you have this external laser, which can rotate with frequency like a few hertz, you can produce the phase slips and the system transfer like a quantum system. It gains a quantum of rotation, and due to this quantum effect, you can tune very, very precisely the frequency of rotation to this transition from zero angular momentum state to the one angular momentum state. This gives this quantum sensor the very interesting perspective, but I will talk about the different stuff now, because it was an introduction. I will discuss, as I promised, some waveguides of matter wave waveguides, but these waveguides can be curved. And why it's important? Because well, in real experiments, you instead of very smooth and predicted waveguides, you frequently gain some curved, really cuspy sometimes distribution of the potential, which affects the flows, affects the dynamics of the condensate. So let's see what happens in this case. And one more additional motivation of considering this system is the so-called quantum bubbles. What is quantum bubble? And the space station, International Space Station, they do some physical experiments, and one of the experiments is the experiment with Bose-Einstein condensates. They have a trap. They can form these Bose-Einstein condensates, but in microgravity conditions. It makes possible to form some kind of bubble. So this quasi 2D system, which attracted a lot of interest because, for example, in this case, it was clearly seen the deformation of the density. So the experiment shows that you have some kind of very clear evidence of inhomogeneities, which appears maybe due to the asymmetry of this bubble, which is not the sphere, it's rather the ellipsoid. And indeed, people try to do it in these works, and we try to see if it happens in why it happens. So we considered, for example, like these waveguides, elliptic waveguides, just to make it simple. And we did clearly see the formation of these density peaks like these. But what happens if you introduce some linear interaction, as I explained you this. In this case, the linear interaction is repulsive. In this case, these peaks are smoothed considerably. And it happens that because of this interaction, and so the conclusion was that indeed such effect is possible, but it's not related to the it's rather the effect of the trap, not the self-operation. But what is even more intriguing in this system, this in curve waveguide, is the effect on the phase. As I told you, if you have this ring, you can create this persistent current, for example, by stirring this laser beam. And what does it mean? If you have this kind of ring, the vortices are trapped in this system. Indeed, if you want to move this vortex outside, you need to overcome the potential barrier, because the vortex, when it crosses the condensate, it includes more and more atoms in this circular flow, and it means that you have indeed kind of potential barrier. It makes these circles, these toroidal traps, ideal for investigating quantum vortices in general, and this persistent current are very interesting. It's very robust and topologically protected state. And what if we will squeeze this trap? What happens then? It's very interesting that this plot shows the density is a surface with additional phase. So you can see that phase has three jumps here, which means you have three vortices inside of the circle. But if you squeeze this system, then what you can see there, the phase gradient accumulates in the region with low curvature. And it means that vortices are squeezed in the small region. And what happens next, if you have a look at the dynamics, I will show you very interesting examples, but let's just mention what this structure resembles so-called solitonic vortices. The story which is described in this paper is very dramatic, I must say. So, the first in experiment, people observed the structure which they treated like dark soliton. What is dark soliton? Dark soliton is the structure which correspond to the phase jump. It's kind of domain wall like this. So at the left you have a phase which has a pi jump between this region, and this is kind of domain wall here. This is the illustration of so-called dark soliton, which means that if you have the density, it's indeed kind of dark region here, okay? So dark soliton. But in experiments, they have seen the motion of this dark soliton, which was very far from theoretical expectations. So the people make different two groups in parallel, made again parallel experiments, and they realized that it was not the dark soliton, it was rather vortex, so which can drift in this elongated trap. So it means that if you have some kind of quasi-1D system, you can expect very complicated dynamics of the vortices. And exactly in our system, what we have seen here is the following. So you can see that if you have, this is the evolution of the phase and these vortices. As you can see, if you start, for example, here with three-charge vortex, this black line is the course of the vortices. After some evolution, you will get one single charge vortex, but in opposite direction. Why? Maybe I can show the video. It's short. I can show you the dynamics of this, like these dots, black dots, green dots are vortex cores. The violet dots is anti-vortex. You can see, so after some time, you have vortex, but again, this evolution transfers this vortex to anti-vortex. So it means that like this, and this happens again, and finally, well, you have the anti-vortex, and after then this system relax to the ground state, and this is indeed kind of example of very interesting complex dynamics, and it resembles kind of rattleback. You know what is rattleback? It's Keldstone. What do you know? What is Keldstone? If you have kind of solid body with specific distribution of the mass, you can rotate it one direction, and after some rotation, this rattleback or Keldstone will reverse its rotation. So you do nothing. You just kick it, and it rotates like a common solid body. But after some time, it oscillates and rotates in backward direction. So it's very interesting effect. Here in quantum system, we have the similar behavior because of the symmetry, of course, of this quantum vortex evolution. Okay, so let's switch to the sensor. Yes, I have the plan to show you how these persistent currents can be used to make some sensors. And one of the idea is to use a linked, we call it kind of quantum flip-flop. What is flip-flop? It's a kind of, if you have this system which can be in two stable states, so it's kind of trigger, yeah? So you trigger the system, and in this flip-flop, you have the one vortex, for example, and you can use some external potential to make some some decreased region with decreased density, and then due to some perturbations, the vortex can drift from one ring to another, and you make the measurement. So if you can see this transfer, this in this flip-flop, you can measure some effects like rotation or maybe acceleration. That's the idea. And indeed, we have seen that such system could be affected by acceleration. But first, let's discuss a very simple system, which demonstrate already interesting physics. For example, here you have this double ring system, and in this double ring system, you create, for example, in the left, you have some vorticity, then you open this gate, and the vortex then can drift from ring to ring, like in periodic motion. And this is affected by the flow motion in these rings, and this flow transfers the angular momentum. So this periodic oscillation has been considered, and with different methods, this is so-called DAM GP, which introduce some effective dissipation. This dissipation is related to the interaction of condensed atoms with thermal cloud, and this is so-called projected stochastic gross-Peters equation, which on top of dissipation includes also some noise effects, and these effects, of course, are connected due to the, so this is the white noise in this case. And also the so-called Zaremba-Nikuni-Griffin model, which accounts on the interaction of the condensate with thermal atoms. And the thermal atoms are described in Boltzmann equation in case of equilibrium state. The Boltzmann equation is just the Boltzmann-Bose-Einstein distribution, and you can calculate the density of the condensate and thermal atoms simultaneously if you assume that these are in equilibrium state. So this was done in this work, and what is interesting that it's again, this gives us the same result, different models. This is the results of, for example, the Griffin model. So this is the condensate and thermal atom distribution. So you have these oscillations, and but if you wait for some time, as you can see, when relaxation state happens, and if you still keep this gate between rings open, then the vortex appear exactly in the central region. So it means that the system becomes very, very sensitive to some external perturbation. So what if you add some external perturbation like acceleration? What happens in this case? Yes, indeed, it was done, and let me show this. I don't know why I messed. Sorry. Sorry for. I have not. Yes. Okay. The message is that if you have the external acceleration, then you make the vortex transfer from one ring to another ring due to the density perturbation. And this resembles like the well-known instrument when you consider the, the surface and you want to avoid some additional bias, you can use this bubble level. In this case, the bubble level is the analog of this system, but instead of bubble, we have the vortex. But okay, let's come back to this. Sorry. Yes, this another system which was considered with the this effect of acceleration, and we consider here not only the effect of acceleration on the motion of the water, but also on the Josephson. I think that you know what is Josephson effect. Yes, just to recall that this effect appears when you have two joint superconductors split by some insulator, the insulator region when you have some tunneling of the Cooper pairs through this barrier from one superconductor to another superconductor due to the phase difference. So this kind of well-known physics here and a lot of technological application of this Josephson effect is known. This guy takes off from Josephson with his famous equation, Josephson equation. In atomic BC, the similar effects can be observed. This is experimental work by Lewis Carstens. They have created some bias of the potential like this, and then they make this symmetry, restore the symmetry, but in the beginning you had some different population. Due to this population imbalance, you have the chemical potential difference, which is analog of the external voltage. And it means that you can create some kind of Josephson effect in this case, and you have these oscillations which are clearly seen, and the frequency of this oscillation is proportional to the chemical potential difference, which is kind of smoking gun of the Josephson effect in atomic BC. So another interesting structure which can be seen in the condensate is the so-called Josephson vortices, which appears due to the phase difference between the counterpropagating flows, for example, here. And this structure can be seen also in kind of ring system. If you have the stack, so stacked vertical stacked rings, you can create counter-propagating flows, for example. And by the way, in collaboration with Anton, for example, we did some work which realized this theory. You can gain the system with a different number of these Josephson vortices. These Josephson vortices are shown here by horizontal black line. So, and what is interesting, if you have these structures, you can see very remarkable dynamics of the Josephson vortices, which drives the dynamics of the, for example, merging rings. Let me show it in detail. So if you have the splitted stacked ring, stack system, you can get the Josephson oscillation that it was shown here. So, example, this is the number of atoms in one ring, another ring. You can see these oscillations, but these oscillations disappear. They are not visible at all if the vortices, Josephson vortices appear there. So it's kind of remarkable manifestation of the angular momentum state in this system. And yes, okay. So this is examples of angular structure of the flow between the rings in the vertical direction. So you can see that if you have the same angular momentum state, these numbers are the topological charge of upper and lower rings respectively, then you can see this oscillation. The color is correspond to the value of the flow through the junction between the rings. And you can see these periodic oscillations here, but if you have the different angular momentum states, then the situation is different. You have this angular pattern, and the flow has the opposite direction, like blue and yellow, top and bottom. And due to this azimuthal structure of this flow, you can see the total flow will be zero in this case. And this is illustrated in this plot. So what is this here? So this is counter-propagating flows in this double range system. And these horizontal lines are jaws and vortices, and they correspond to the tunneling flow, which was numerically extracted from the simulations. So you can see this very nice illustration of the jaws and vortices. And if you have sorry, I don't know these jaws and vortices, they can move in rotate due to the chemical potential difference. But I think that most sophisticated evolution happens when you have merging rings. For example, here you can control the wave, switch off the barrier between these rings, and this is shown the barrier amplitude as a function of time, dash line, and the energy of the system. Of course, if you decrease the barrier, so you change the potential and the total energy decreases, but after some time you relax to the sun state. So the idea is to see what happens if you have, for example, counter-propagating flows and then you make them merge. What happens then? Okay, if you have the classical system, what do you expect? If you have counter-propagating flows, you merge them, and the final state, of course, is a non-rotating state. Yeah, so it's clear. It's clear, but it's completely wrong in quantum system. Let's see what happens here. This effect, by the way, resembles the Kelvin-Horn stability in classical and quantum system, which illustrated in these plots. What is Kelvin-Horn stability? When you have the counter-propagating flows, or at least you have different velocity of the flows at some threshold, sometimes threshold without. Here you have formation of the vortices, like in classical system and quantum system. But what happens here is remarkable that in this case, you gain the final state, which is not zero, practically never zero angular momentum state happens. And this is the manifestation of the quantum effects. For example, here you have two asymmetric systems. One has a very small number of atoms in the upper ring and large atom in the lower ring. If you merge the system, after some time, you will get this state which has the same angular momentum as a large ring. It's not a big surprise, but if you have nearly the same number of atoms in both rings and you make them merge, then the system will tend not to the zero angular momentum, but to the state which is a little bit lower number of atoms. So it's very clear from the evolution of the system, but it's counterintuitive from classical prospects. So that kind of interesting effect in this system. Okay, and remarkable quantum structure appears if you have kind of elongated state, elongated rings like this. And what you can see here, if you merge this system again, then these jaws and vortices, they stay kind of horizontal structures. They do not change the orientation. And finally, you get some very long-lived quasi-stable structure. It's still degrades after a few seconds, but it's really stable structure during this time. And this is kind of hybrid structure because the total angular momentum is zero because you have counter-propagating flow, but you have very complicated topological structure of these flows, which resemble so-called hybrids, which was predicted in the similar system. But in this case, this is very simple and in experiments it can be realized. So And by the way, these jaws and vortices, they resemble some vortices which you can find in different classical quantum systems. For example, this is famous red spot, great red spot, which is formed by azimuthal flows of atmosphere of Jupiter. And this kind of storm, this crazy red spot, it's huge and it survives for 100 years, like 300 years is observed in the Jupiter. And also these Johnson vortices can be seen in, for example, in superconductors, and they are used, of course, not for magnetic sensing, and also there are some projects which use these magnetic fluxes as fluxons. This is another name of this Johnson vortices in kind of qubit as well. So this is the conclusion. So this coupled rings suggest very interesting dynamics related to the Johnson physics and Johnson vortices. And another system which we discussed today is a planar a system which was realized in many experiments. These are some examples from different experimental groups, from Florence, from Australia. I don't remember exactly, but this is a link from Darmstadt group from East in US and also again in Australia. So a lot of different groups created this double ring system, and we consider the physics which is related to the persistent current in this system. And what is remarkable here, that you again have the Josephson oscillation, which uh, can be affected now by acceleration, as you can see. For example, here you have the double ring system with the same angular momentum state. In this case, you have, due to the chemical potential difference, you have the transfer of the flow through the barrier. This is Josephson effect. These oscillations are clearly seen in this diagram. This is imbalance as a function of time. But if you have the different angular momentum state, these oscillations are suppressed, so the total flow through the junction is zero. But if you have the acceleration like here, the acceleration is directed from left to right, then the density a little bit biased. So it means that this symmetry is not pure now. So you have some asymmetry. And due to this asymmetry, you can excite additional modes like this, and you can see the effect of these Josephson oscillations in accelerating frame. So what is important here that indeed we have some effect of acceleration on the dynamics of this flow. Okay, but maybe we can clearly use this for measuring acceleration. Yes, in fact we can, and this is because if you have the accelerated ring like shown here, due to this bias, you have kind of potential well, or shown here. This is potential well of the vortex, which is trapped between these rings. So the red dot shows the vortex, goes vortex between these rings. Due to the acceleration, the potential well may gain deeper and deeper, and finally you can expect that the vortex will be elongated, so will has a tendency to move to the bottom of this potential well due to the relaxation. So relaxation means if you have some weak dissipative effects, after some time the vortex will tend to align in direction of acceleration like this, even this acceleration is very small. Okay, so let's see how it works. And this is illustration of the vortex dynamics in accelerating frame. So you can see this dot and phase and density. Even in density, you can see this density dip, which indeed tends to the direction tends to the state which is directed along the external acceleration. And this position doesn't depend on the carry. It depends only on the acceleration. So this one box. This kind you can see the direction of acceleration, but what about the magnitude of the acceleration? Is it possible to find the magnitude? The answer is yes. You can, and so to do this, you need to use more vortices. For example, here we have a lattice of vortices which are shown here by these red dots. If you have no acceleration after some relaxation period, you will have kind of lattice inside of this structure because you have the interaction between these vortices and they tends to form some hexagon system. And this hexagon will be deformed if you have the external acceleration. Indeed, as you can see here, these vortices drift in this effective potential. They change the position, and if you calculate the total shift, like center of mass of these point-like objects, you just calculate this using a very simple formula like this. What is this? This is the kind of asymmetry parameter, which is related to the position of the vortices. And if it's zero, then we have no deformation of this lattice. Okay. So what happens if you apply the acceleration? Then you can see that deformation asymmetry parameter tends to some value after relaxation process. And this value, which is shown by a dashed color line in the inset, it depends on the acceleration only. It doesn't depend on the dissipative rate, but it depends on the acceleration. So if you just make some simulations with different acceleration rate, like here, it's shown in millimeters per second squared. So you can see that for small acceleration rate, you have very simple linear fit to this dependence of symmetry parameter as a function of acceleration. So this means that measuring this deformation of this lattice, you can calculate what was the deformation of this lattice related to the acceleration. So you can use it for like an element for measuring acceleration. Okay, so the role acceleration in the system which we have considered today is twofold. For example, here we have the effect of acceleration, which tends to kick one vortex from ring to ring. So this is kind of linear acceleration sensor. And another approach was using Josephson vortices, which are related to the such system like this. And this system resembles the circular bubble level, which allows measurement both direction and the magnitude of the external acceleration. So okay, so I think that this is the end of my story, and I think that we can just we have some time for questions and discussions, and I will be happy to answer your question if you have any comments, questions.
So any questions from the audience?
Just a moment. Yeah, do you have questions? Yes, Anton, we do have question. Let me.
Thank you. So I have kind of two questions. First one is related to toroidal Bose-Einstein condensate. You told that we can rotate this toroidal condensate using lasers. Can you tell a little bit
Yes,
how it's performed and how?
Yes, like this. Yes, it's very good question. So if you can rotate something superfluid, yes, how to do that? In fact, it's not kind of the truly rotating, it's kind of stirring, yes. So in experiments, they do the following. So first they create the trap, which makes atoms type in donut. Yes, so it's squeezed in vertical direction, but it's a donut. Then they applied additional laser beam, which moves like this. So let me draw it a kind of snapshot what they do in experiment. Can you see my drawing?
Yes, we can, but not so good.
Okay, let me use another instrument like this. I think it's better. So this is this toroidal condensate, which is trapped like this, and they use kind of additional laser beam like this, which scans in radial direction with a high frequency, like 2 kilohertz. This is very fast radial direction. In radial direction, it's fast. And simultaneously, it moves in azimuthal direction, like shown in this movie. Yeah? And what people can control? They can control two parameters: the amplitude of the laser beam and the frequency of angular velocity, which is associated with this azimuthal stirring. Okay, and if you consider the different Berea amplitude, you will see the different critical angular velocity of this transition, how it works. So let me plot. If you fix Berea amplitude and you change the angular velocity, and then you make the measurement of the angular momentum state. What does it mean? If the angular velocity below some critical value, the final state is zero. So the topological charge is zero. Okay? But if you change the critical, the angular velocity below the critical value, then it jumps. It jumps why? Because the vortex comes through this weak link. What this, as you can see, the density is not homogeneous in azimuthal direction. Yeah? It means that in this weak link, the vortex can transfer from outside to this hole, and this is associated with this phase slip. So what people do, they tune the barrier amplitude for different angular velocity, and then you can tune it to such a value which is very specific to this barrier amplitude. So it means that it's kind of tunable quantum rotation sensor. Okay, so the idea is to make this stirring laser beam with amplitude which can tune the critical velocity for critical angular velocity for this transition. And if if you want more details how this happens, for example, if you come to the details to this region, then the flow through this weak link appears in such a way that the vortex dipole forms in this weak link region, and then the phase slip associated to this dynamics of this vortex dipole. So this is quantum effect, and it associated to the quantum transition between angular momentum states. And this is well described by the simple theory, but but has not too good correspondence with the experiment for the moment. So, and it's kind of puzzle yet, I must admit. But the idea is as following. So yes, in experiments they use a stirring beam. Okay.
Okay, thank you. And I have another question.
Yes.
I wanted to clarify the plot. So the plot which I wanted to ask about is about the merging of two vortexes.
Yeah. Two rings. Yes.
Yes.
Okay.
Um,
Here.
Next one, I think. One. Go on.
Before.
And I think it's in somewhere in this one.
This one. Okay.
So
Yes.
I wanted to just clarify. So I thought you said that I cannot see what's like axis names. So if I understood correctly, the x-axis is the like distance between these vortexes, and the
You mean the
y-axis.
right hand side? Yes.
Yes.
At the right. Okay.
Yeah. So
sure.
And if I understood correctly, the color is the velocity space. So does they have different? Yes, these plots.
Okay, let's discuss these plots. Yes, let me describe. Thank you for this question, because I had to explain what is this indeed. So what is a vertical coordinate is z. There is a vertical coordinate like here. And what is the horizontal axis is the distribution of this is a density, the color-coded density, yeah, along the angular coordinate. So you just make this cylinder and then you cut it and make kind of such a plot. Yes. So I mean this point and this point are the same point. Yeah. So I mean this is kind of strip, yes, which you just put on the plane. Okay. So you see these crosses, and these crosses are Josephson vortices, which are shown here. Okay. And so this is basically the angular coordinate. So the phi dot r0 is the radius of the cylinder. Phi is the angular coordinate. So this is the distribution of the density along the peak density region. So this is kind of the left plot, and this is the phase of wave function. And the phase illustrates the position of the vortexes. You can see these points. If you make the circle around this plot, the phi has 2 pi jump. Yeah, this is the vortex. And it's clearly seen in the density distribution. And if you're asking about the plot, what about the direction of the flows? They're also shown here by these lines with arrows. Yeah, so I mean that arrow shows the direction of the flow. If you can see it, I don't know. Okay.
Actually, I do not, but okay, I think I'll can check presentation later. Yes.
Okay. Yes. Sure.
Okay. Thank you.
You can find you can find the links to the papers.
Okay, thank you. Other questions from local audience? Anton, from online maybe have?
No questions from online.
No questions from
Audience.
online, yeah? Okay. Will somebody ask question? Not at all. Okay, then we can thank speaker.
Thank you.
Thank you very much for such interesting and informative lecture.
Thank you.
Okay, yeah, thank you very much.
Yeah. Thank you very much, Oleksandr.
Thank you
So
for that.
now
Thank you.
we have lunch time.